In this lecture, we're going to examine Earth's climates and major terrestrial biomes. Biomes are specific portions of the biosphere that's determined by a climate, precipitation, temperature, and a predominant vegetation and organisms that have evolved to live in this particular environment. There are three broad categories based on climate, and these are marine, freshwater, and terrestrial biomes. In this lecture, we're going to talk about the terrestrial biomes that are found on Earth. Biomes themselves, we can further divide them based on the ecosystems, the interactions between organisms, and their surrounding abiotic environment, so water, rain, sunlight. Much of the Earth's climatic variation is caused by the uneven heating of Earth's surface by the sun. And this uneven heating is a result of the Earth's spherical shape and also the angle that it rotates on its axis as it orbits the sun. The latitude north and south at which the sun is directly overhead changes with seasons. And this seasonal change occurs because the Earth's axis of rotation is not perpendicular to its plane, and it's actually tilted about 23.5 degrees away from the perpendicular. As a result of this tilt, on June 21st, the sun is directly overhead the Tropic of Cancer at 23.5 degrees north. On December 21st, it is directly over the Tropic of Capricorn at 23.5 degrees south. In September and March 21st, September 23rd, the sun is directly over the equator. And so because of this seasonal variation of where the sun is located, proximity to different points on Earth, you get these seasonal variations as you go north and south from the equator. The other major factor that controls the different biomes and climates on Earth is the Coriolis effect. We know that the Earth rotates on its axis, and because of this rotation, it causes this apparent deflection of winds and water to the right in the northern hemisphere, so they swerve towards the right if you're facing down towards the equator, and if you're coming in the southern hemisphere and going towards the equator, you would be swerving towards the left. And this causes the prevailing winds all over the globe, and we'll describe these in the next slide. These are the polar easterlies, the westerlies, and the trade winds. This heating of the Earth's surface by the sun is going to drive circulation through the atmosphere. So in March and September, when the sun is directly over the equator, or whether you're talking about June or December when it's directly over 23 degrees north or south latitude, most of the sun's energy is going to be focused in this area on the globe. And as a result, you're going to get these uneven heating patterns. At the equator, you're going to get a lot of the sun's energy at the surface. This air is going to heat up. As a result, it's going to rise and expand. As it rises, this air is going to cool. It's going to produce rain, and that's why you get quite a bit of rain here at the equator in what we call the ITCZ, or the Intertropic Convergence Zone. As this air is at the higher elevations, it's going to cool and it's going to spread towards the South Pole and towards the North Pole. As it spreads, it's going to become more dense and sink, and then at 30 degrees north and 30 degrees south, we have cold air coming down. Again, this is going to spread towards the poles here and towards the pole here. It's going to pick up energy from the sun, the Earth's surface. It's going to heat up, and you're going to get this convection or air rising at 60 degrees north, 60 degrees south, and then finally at the poles you're going to get this high pressure system as this cold air sinks at the South Pole and at the North Pole. And because of the Coriolis effect, you're going to get different wind patterns. You're going to get the trade winds that are blowing towards the equator. They're deflecting towards the right in the northern hemisphere. They deflect towards the left in the southern hemisphere, again because of the Coriolis effect. Then you're going to get these westerly patterns between 30 degrees north and 60 degrees north. You're also going to get these westerlies between 30 degrees south, 60 degrees south, and then finally the polar easterlies flowing between 60 and 90 degrees south and between 60 and 90 degrees north latitude. And so this diagram really shows what's going on when you have the uneven heat exchange and you have the Coriolis effect. You get a low pressure system at the equator because you have warm air rising, and so you have a low pressure system. Because of the Coriolis effect, it's going to cause this deflection in the counterclockwise rotation. At 30 degrees north, you're going to have cold air coming back down to the surface of Earth, so you're going to have a high pressure system. In the northern hemisphere, this rotates clockwise. At 60 degrees north, you're going to have a counterclockwise low pressure system, and then at 90 degrees north, you're going to have a clockwise high pressure system. And the opposite is true as we move into the southern hemisphere. High pressure systems in the southern hemisphere rotate in a counterclockwise direction, so you'll have a high pressure system at 30 degrees south and a high pressure system at 90 degrees south. You'll have a low pressure system of warm air rising up into the atmosphere at 60 degrees south. And then, of course, you're going to have the westerlies here, and the trade winds near flowing into the equator, and then the polar easterlies flowing out of the poles. And you'll notice that the wind patterns in the northern hemisphere, you're going to have a deflection of the wind towards the right in the northern hemisphere and a deflection of the winds towards the left in the southern hemisphere. And again, this is caused because of the Coriolis effect and the rotation of the Earth on its axis. If we look at the major surface currents around the globe, you can see again this is caused because of the Coriolis effect. In the northern hemisphere, you're going to have a clockwise gyre or clockwise rotation. And in the southern hemisphere, you're going to have a counterclockwise rotation at the surface of the oceans. So the oceans are very deep. So not only are we concerned with what's going on with the currents at the surface, but we have to remember that there's going to be circulation of this marine water throughout the water column. So you're going to have circulation at the surface. You're also going to have circulation deep at the bottom of the ocean. And that's what we see here. Here near the equator, we have this warm, less salty, shallow current. As it migrates towards the North Pole, it's going to cool and become more dense. It's going to sink. So this cold water is going to travel again down across the equator, down towards Antarctica. This is very deep current. It's going to continue to travel and then back up to the equator where it's going to warm up. As it warms up, it's going to rise. And again, you're going to get this ocean conveyor belt that exists on Earth. The other factor that's going to control climate is mountains, orographic effects, and that can be seen here in these diagrams. This is what you would see near Seattle, Washington, for example. You have the Pacific Ocean here. Here would be Seattle, Washington, and then here you have the Cascade Mountain Range. As the prevailing winds come off the Pacific towards Seattle, they're forced up the mountainside. As they're forced up, they become more dense, and this water that's in the atmosphere falls as precipitation. That air then can go over top of the mountains and you get this rain shadow effect on the other side. So you can see this near Seattle, Washington. You can also see this in the Himalayas and the Tibetan Plateau. As the warm, moist air comes to the Himalayas, it's forced to go over the mountains. As a result, all the precipitation is dropped on this side, and you can see it's very green. You have a lot of vegetation on this side, and then you have the rain shadow effect where you have deserts, very arid climates on this side, and this is caused because of the orographic precipitation.